In this video, we're going to talk about light and nutrients. Nutrients are a key component of life in the ocean, of the biology of the ocean. The biology in the ocean is going to be the focus of modules 6 and 7 later in this course. So in this video, we're just going to concentrate on the role of light. So you remember from the video on light penetration that we saw that light didn't penetrate too far into the ocean, blue light penetrated the furthest, and by, depending on the conditions of the ocean, 100, 150 meters, we were down to about 1% of the light that was incident on the top of the ocean. So this figure shows the ocean depths broken up into different light zones. So the upper ocean, here they have it down to 200 meters. You have sunlight tapering off exponentially from the surface down. So that's known as the euphotic zone, where there's sunlight. And for most of this zone, photosynthesis can occur. The next layer down is the twilight zone, where there is a very, very, very small fraction of light that can make it down there, not enough to do photosynthesis. Then we have below that the aphotic zone, so below around 1,000 meters, where there is no sunlight at all, completely pitch black. So the focus of this video is on nutrients. Nutrients are a non-conservative element that's used by organisms, by biological organisms. We'll see in the video on salinity that there are conservative traces as well, which do not change throughout the ocean. Nutrients can be broken down into a couple of different classes. There's essential nutrients, which are required for soft tissue. Essential nutrients include carbon, nitrogen, phosphorus, and oxygen. And then there are a bunch of nutrients that are required, but in very small amounts. So these are known as the micronutrients. And they include magnesium, iron, selenium, and a bunch of other ions. So what are sources of nutrients to the ocean? Well, carbon comes from CO2 in the atmosphere. The most common gas in the atmosphere, we'll see in another video, is nitrogen, N2. Unfortunately, this form of nitrogen cannot be used by any biology in photosynthesis. So it needs to be fixed into either nitrate or ammonium. And most of this fixing happens in situ in the upper ocean by nitrogen fixing bacteria. Some is recycled and comes into the ocean from rain or from river input. Phosphorus comes from the process of rock weathering. So it enters the ocean via rain or via rivers. And iron, which is one of the micronutrients, comes from dust clouds from the continent, so primarily from the deserts of the world. Here, the red is high dust concentration, and the blues are very little dust concentration. So nutrients are used in photosynthesis. So we have the nutrient ions, so phosphorus, nitrate, etc. Photosynthesis, the process of photosynthesis, uses sunlight and photosynthetic phytoplankton in the ocean to create organic matter. And then this organic matter is used by other organisms that aren't photosynthetic, like us, fish, and we respire that organic matter. So we take the organic matter in, we breathe in, and then we combine the oxygen with the organic matter and release nutrients again. In the ocean, photosynthesis can only occur in the light layer, the euphotic zone. Respiration can occur in both light and no light layers. Nutrient profiles vary greatly with depth. Because the photosynthesis occurs in the upper ocean where there's light, the nutrients are being drawn down as they're being converted into organic matter. So we have low nutrients near the surface, and then as we get deeper into the twilight zone, we have respiration going on, nutrients being returned to the water column, and then below that, at least around Hawaii, there's a slow decrease in the nutrient concentrations. So this figure shows depth on the vertical axis here. It's from a station north of Oahu, where there's been a time series over the last 30 years. And then we have concentration of nitrate on this plot and phosphate on this plot, and you see that both nutrients have the same vertical profile. If we look at sections through the Pacific, so we have here a section from a big experiment that happened in the 80s and 90s, 1980s, 1990s, and they did a section from Alaska down to almost to Antarctica. So in this plot, we have the South Pole over this end, northern latitudes over this end, the equator in the middle here, and this top plot is nitrate concentrations throughout the depth of the ocean along this line. And the bottom plot is phosphate, again, versus depth and latitude. So you'll notice that near the surface, there is very low nutrient concentration, both nitrate and phosphate. And then in the northern hemisphere, it goes up to more of a maximum around 1,000 meters, which we saw in our profile from Hawaii. Southern hemisphere has less of an increase, but it's still obviously lowest at the surface. You'll notice that in the mid-latitudes, the layer where there is low nutrient concentrations is deeper than at the tropics. We'll see later that this is because there's a layer that is well mixed, and in the mid-latitudes, there's a lot more storms, so you get a lot more mixing, so you get a deeper, what's known as the surface mixed layer. Where in the tropics, we get a lot more solar heating and a lot less storms, which allows it to form a much thinner surface mixed layer. So we saw that near the surface, the nutrients go to nearly zero. So do all nutrients go to zero at the same time? The answer is no. So here in the nitrate plot, we see that they do go to zero right here for the top 100, 150 odd meters, that all the dots here, which are individual samples of nitrate, go to zero. Whereas on the phosphate plot, they don't. So you can see that there is a bit of white between the axis and the data points. So they don't all go to zero. Some go to zero, some don't. So why is that? Well, there's this ratio of how much different nutrients you need. For every one phosphate atom, you need 16 nitrate atoms and you need 106 carbon atoms. So if you have, say, 2 phosphorus atoms available to you, you would need 32 nitrate and 212 carbon atoms. And so here, briefly, we have 106 carbon atoms from CO2, 16 nitrogen atoms from nitrate, and 1 phosphorus atom from phosphate. And that creates an organic compound here and releases oxygen when you're doing the photosynthesis, which is traveling right to left. The respiration, which releases the nutrients, goes from left to right. So you take organic matter, oxygen, you release CO2 and a bunch of nutrients. So that means that in any area of the ocean, when one nutrient profile goes to zero, biology organisms can't use the remaining nutrients. So here we have this being nitrogen limited. So nitrogen has gone to zero, and there was more than a 1/16 of the number of nitrogen atoms of phosphorus atoms. So that nitrogen is gone, but there's still some phosphate left because nitrogen is what's known as the limiting nutrient. So it's the one that goes to zero. You also notice that, around Hawaii, nitrogen goes to zero down to around 150, 140 meters. So why is that? Well, 140 meters is the extent of the light penetration, down to about 1% of the light entering the ocean. So photosynthesis has been shown to occur down to the level where there's 1% of the light left from what's hitting the top of the ocean. So you can see here that the light decreases exponentially, and then when it gets down to 140 odd meters, it's less than 1%. And then because it's exponential, this will slowly tail off through the twilight zone until you get down to the aphotic zone.